Okay.
Thank you.
You can see the first paragraph. Yes. I recently finished a paper that is available on the archive with the same title as this talk. And I'll basically in this talk, I'll be giving an overview and a report on this talk. Just in case you happen to wish to at some point refer to this paper, I'm just in the process of submitting a revised version. So you may want to wait for a few days in case you want to download it. But the current version there will do the purpose of getting more detail on what I'm going to be talking about. So the revision is just basically on just some fine tuning, nothing major. The talk is focused principally on a system of set theory formulated in a language that has two extra symbols in addition to what set theory uses. You know, as we know, ordinary set theory just uses equality with epsilon. In this system, we have a global well-ordering of the universe as a less than symbol that you see, and also a unary predicate, which will be eventually denoting a proper class of indiscernibles, which I will describe exactly what that means. The motivations for considering such a system is briefly visited in the introduction of my paper. So at this point, I will not motivate this, but I'll be glad to talk about it maybe later in the talk if there are any questions about the motivation for such a system. I will just suffice to say that it tries to capture a maximalist view of set theories as opposed to a minimalist view. I had looked at systems of set theory which are, I would call Leibnizian in the sense of having items in the universe that have that can be distinguished from each other, and this system basically goes the other way. It thinks of the universe of set theory as being so rich that it has a proper class of indistinguishable objects. I will also say a few words about the a twin system, which is obtained by adding a unary predicate to Peano arithmetic. Here, we don't have to add less than to Peano arithmetic because Peano arithmetic already comes with a global well ordering. And it's very interesting to compare and contrast these two systems, PAI and ZFI. I will first walk through the main results of the paper, describe what they're saying, and then I'll, in the next stage, look at how some of these results are proved. That's pretty much my approach to how we're going to go through the talk. So first, the first theorem in the paper characterizes the first order consequences in the language of set theory, ordinary set theory of this supersystem. So we have this supersystem ZFI with less than, and we want to see what are the theorems of ordinary set theory that it proves. So it turns out it proves precisely those sentences that are proved from a strengthening of set theory. That's ZFC plus capital lambda. Lambda is in honor of Azriel Levy, who in a number of papers studied reflection phenomena in set theory, and in particular Marlow cardinals. So this lambda is a scheme. It consists of sentences lambda sub n for each natural number n. And lambda sub n is a sentence, a single sentence which asserts the existence of an n Marlow cardinal kappa, such that V kappa, the initial segment of the universe up to kappa, is a sigma n elementary submodel of the universe. So you see this n twice then in lambda n. Basically, it refers to how Marlow is the cardinal that you're asserting to exist, and also the fact that it's a sigma n elementary submodel. Now, it happens to be not really important for these two n's to match. You could actually have a scheme which has two parameters, maybe m and n, where n tells you how Marlow is the cardinal, and m says how reflective it is. And that happens to be, if you write such a scheme, which basically, for example, would say there is a 10 Marlow cardinal that is 35 reflective, then you get the same scheme as this one. So it's actually very robust. This one is nicer to be able to write down. Now, let me say.
Could you perhaps remind us? Sorry. Could you perhaps remind us what is an n-malo cardinal?
Precisely, and that's exactly the next slide, actually. Yes. The notion of an alpha malo cardinal is defined recursively, where alpha is any ordinal. So zero malo cardinals are precisely the strongly inaccessible ones. So, and then if you have an any ordinal alpha greater than 0, then alpha malo means that the collection of beta malos below, for each beta less than alpha, the collection of beta malos below kappa are stationary in kappa. So stationary in kappa, as you remember, means it's not only unbounded in kappa, but it meets every closed unbounded set in kappa. So in particular, one malo cardinal is a cardinal whose set of inaccessibles before it is stationary in that cardinal. A one malo cardinal is much stronger than just malo. Okay. And then classically, it's known that they form a hierarchy, and one way to transcend this hierarchy is to, for example, go to a weakly compact cardinal, which is kappa malo, but it's above the first kappa malo. So, but it's important for me to focus here on the fact that in ZFC, weakly compact cardinals, which I'll review the definition a bit later, have the property that there are not only one malo, two malo, three malo, but they're actually alpha malo for every alpha less than kappa. But in the scheme, we always, let me go back to the scheme. As you see, it only talks about n malo for concrete natural numbers n. Please, of course.
Okay, we dealt with kind of similar notions, but let me check my understanding. So,
yes.
Would it be the same? So we know what is a malo operation. Would it be the same definition that we take this, let's say, class of strongly inaccessible cardinals, and then apply to it malo operation alpha times? That's more or less what the notion alpha malo means here.
That's
okay. Okay. Good.
And then we can look at a fragment of this scheme. This scheme, as you remember, had two parts. It basically said that we have reflection at a particular level of malo-ness. But if you just look at the fragment which says for each concrete natural number n that there's an n malo cardinal, then I'm going to refer to that as lambda minus. It just says there's a one malo cardinal, there's a two malo cardinal, without saying how reflective they are in the universe. So this theorem that I'm about to walk through is folklore. It uses classical techniques in set theory, most of which are due to, if not all, to Asriel Levy. The notion of omega malo, for example, can be described as follows in an equivalent way. If you pick any subset of V kappa, epsilon with this added predicate satisfies the extension of that lambda scheme where it's allowed to mention the parameter x. So if you so here we just basically refer to what kind of theory does this structure satisfy, as opposed to an iterative definition. The intuition is that the scheme lambda that I had on the first slide is expressing that the class of ordinals behaves like an omega malo cardinal. Maybe that's the intuition I want you to take from lambda. The lambda is trying to say in a first order way through a scheme that the class of ordinals behaves like a one malo cardinal, two malo cardinal, three malo cardinal, and so intuitively like an omega malo cardinal, except that the universe might be omega non-standard. That's why we have the scheme as opposed to one sentence. Now, this scheme lambda minus at the consistency level is actually at the same level as lambda. It's mutually interpretable even with ZFC plus lambda minus and ZFC plus lambda. So for example, this lambda minus occurs in a lot of work of Harvey Friedman when he's got all these independent statements that he shows are independent. And often these n monocardinals play a role in his theorems. But here we have, I mean, lambda is actually what we need, the scheme lambda, not just lambda minus for the work to go through. And part C is just basically saying that if you just have enough large cardinals around, this scheme lambda minus is truly weaker than lambda. So this fragment is truly weaker, which you would expect that. Otherwise, I would have used lambda minus. Now, this scheme is very robust, lambda, this Levy scheme lambda. It is inherited by the constructible sub-universe of the universe. So if you have a model satisfying it, and if you go to the constructible universe of that model, that constructible universe sitting inside that first model will also satisfy lambda. And it's also outward robust. If you have a model of set theory satisfying lambda, and you have a set notion of forcing, and you extend the universe through a generic filter M of G, then M of G, the generic universe, also satisfies lambda. So it's inherited both by inner models and outer models, but when it comes to outer models, we have to be careful because the notion of forcing has to be a set notion of forcing. Part E is not true if you allow class notions of forcing. Okay.
There was a question about notation. So V of kappa, is it the same, means the same as V kappa?
Yes.
Yes. Okay.
Thank you for asking that. Yeah, I end up using this notation because often I have to use models like M sub 1, M sub 2, etc. So I put the kappa in the parentheses as opposed to a subscript. That's right. So V kappa is just what we ordinarily write as V sub kappa. Yeah.
Okay.
So it is known, and this goes back to a 2004 paper of mine, that the purely set theoretic consequences of Gödel-Bernays set theory plus class form of axiom of choice, that's the GBC you see here, plus the statement that ordinals form a weakly compact cardinal as a class, the first order consequences of this system of class theory coincide with ZFC plus lambda. Let me pause for a second. I'll say more about exactly this GBC and orders weakly compact. But so here we have a system of class theory, which is basically conservative over ZFC plus lambda. One could say the analogous thing one usually sees is that GBC by itself is conservative over ZFC, just like ACA 0 is conservative over piano arithmetic. So here we have basically the first order part of GBC plus orders weakly compact is precisely lambda. So lambda has arisen before as a canonical theory in this earlier work of mine, and it's appearing again in this other context that you're seeing today. Now, what is this theory GBC plus orders weakly compact? Well, GBC, I won't say anything in detail except to say, again, to remind you, is Gödel-Bernays class theory, and the capital C denotes that you have a global form of choice. It's a system that was first studied by McAloon and Rosser in a paper of 1981, and then later, with different methods and motivations, I studied it in this 2004 paper, and then more recently in this paper that I'm talking about today. When you see the quotation, the quoted statement, orders weakly compact, is a single statement, it's not a scheme. It's one sentence in the language of class theory, which says that every ordinal tree has a branch. Now, an ordinal tree is defined in analogy with the kappa tree in infinite combinatorics. An ordinal tree, it means it's a well-founded tree of height ord, such that the collection of nodes of any prescribed ordinal rank is a set, as opposed to a proper class. You have an object, which is a class. It's ordered like a tree, and each initial segment of it, well, first of all, it's a tree, it's a well-founded tree of height ordinals, but each truncation of it is a set. So usually such an object is called set-like. Before I look at this theorem, let me just pause to say, if you think about this statement, the analog of this statement in arithmetic, then this would say omega. First of all, what I mean by the first order, the arithmetical counterpart, think about ACA 0, system of second order arithmetic where you can talk about subsets of natural numbers. Then ORD is weakly compact in that context would basically, ORD in that context is just the class of natural numbers. And what you're seeing basically, ORD is weakly compact is none other than Koenig's lemma, which says every infinite tree that is finitely branching has an infinite branch. So here we have to add it to GBC as opposed to it being a theorem. It's not a theorem of GBC that order is weakly compact, as it turns out. So here are some reformulations which shouldn't surprise you if you think about equivalent formulations of weak compactness or even different ways of thinking about the arithmetical counterpart. The tree property, which says, so the following are equivalent if you give me a model of GBC, to say that every ordinal tree has a branch is the same as saying that the Ramsey property holds for an arbitrary set of colors and an arbitrary meta-theoretic exponent. And that is basically what you're seeing in this Erdős notation, ordinals arrow, ordinals super n, where n is some concrete natural number, hence meta-theoretic natural number. And kappa is some internal cardinal. And also you can weaken it just to exponent 2 and 2 colors. So that would be just ORD arrows or 2, 2. So the statement ORD is weakly compact, if you want to just take away a quick definition, you can take this last equivalent, that ORD arrows or 2, 2, or that the ordinals satisfy Koenig's lemma, that if you have a tree which is set-like, then it's set branching, and it's a class tree, then there's a branch through it. So that finishes my summary of what theorem A was saying. I, of course, haven't given you any idea about the proof of it. As far as the other results, the other theorem that these are the main theorems in the paper is that if you have an omega model of this system ZFI with less than, which I haven't given you the axioms for yet, but basically just think of it as this enriched system of set theory, which has indiscernibles. If the model happens to be an omega model, meaning it doesn't have any non-standard integers, then that model actually satisfies a strong form of V is not equal to L. The universe is not constructible. So it's truly, one feels a sense of transcendence here, that you have a system of set theory which assures you that V is not equal to L. However, this is only if you have an omega model. It turns out this omega model bit is really crucial because this theorem is false without with the omega model bit. And then if you look at this blue sentence, which is a single sentence in the language of class theory, this sentence is not provable even if you assume that the ordinals are weakly compact. Now, I want to motivate theorem C by reminding you of the arithmetical counterpart. Well, first of all, to fully appreciate theorem C, first one has to note that GBC, there's a little typo here, sorry, meaning misprint. This GBC cannot prove this. GBC plus ORD is weakly compact can prove this statement, ORD arrows, ORD NM. So this enriched GBC can prove each concrete instance, ORD arrows, ORD NM, but it cannot prove this universally quantified sentence.
Okay.
Yeah. And if I go through the arithmetical story very quickly, in the 70s, Jokic proved some nice results about how recursion theory interacts with Ramsey theory. And then shortly after the appearance of his paper, both him and Solovey noticed that the results of Jokic can be shown to demonstrate that ACA0 cannot prove this form of Ramsey's theorem, the quantified form of Ramsey's theorem, that for all m and n in omega, then omega arrows omega and n. Now, this is, for some reason, less known than it should be, this arithmetical fact, because it was overshadowed by Harris-Harrington phenomena not long after that. So this unprovability of the quantified version of Ramsey's theorem in a way foreshadowed the unprovability of Harris-Harrington, which was done a few years after that. Okay, now let's look at this next result, which is what I consider a main result because it connects, it's something about PAI, the arithmetical counterpart of ZFI. So you have Peano arithmetic with indiscernibles. It turns out it's almost the same, this theory is almost the same as a truth theory known as UTB. Let me see, maybe before I go to the corollary. So UTB stands for, let's see, the uniform Tarski biconditionals. So this is a truth predicate which satisfies a uniform form of Tarski biconditionals. Another way of actually talking about UTB is to think of a truth predicate which, first of all, is inductive in the sense that if you adjoin this truth predicate to the model M, then in the extended language, you still have induction. And second of all, it satisfies Tarski's conditions for a truth predicate, the recursive conditions for all standard formulae. So this is a well-known system of truth theory that people have studied, both in truth theory and also in models of arithmetic. And it's known that every model of Peano arithmetic that is recursively saturated extends the model of UTB. And in particular, so this shows that PAI is conservative over PA. So this is in contrast with ZFI, which is not conservative over ZF in the formulation that I had. So here we see a big difference between Peano arithmetic and ZF. ZF basically, the ZF version of the theorem is that ZF, when you adjoin, if you have ZFI, theorem A says that it's conservative over ZFC plus this lambda scheme, the scheme of the existence of n-reflective n-molar cardinals. By n-reflective, I mean V kappa, such that V kappa is a sigma n elementary submodel of the universe. And that also model theoretically, it shows that the models of PA that have an expansion to PAI are precisely the recursively saturated ones. I will outline the proof of this theorem shortly, so I'll say more about this theorem. So now we get to see officially the axioms of ZFI. So notice I'm first going to define the axioms of, actually what you'll see is the axiom of just ZFI. When I write ZFCI, I simply mean that you also have the axiom of choice. So I have two systems. One is just in the language of set theory plus this predicate I. And then I have another system which you also have this global well ordering. So there are just, one is the variant of the other one. But let's first look at the version which is in the language of set theory adjoined with, so this L set parenthesis I means you have added a unary predicate to the language of set theory. So in this language you have equals to epsilon and also I. Okay, so I would also write down X as a member of I instead of just I of X. So the first group of axioms in this system of set theory is ZF in the extended language. So in particular, the collection scheme and the separation scheme can use formulas that mention I. Intuitively, it means that I can participate in set theoretic reasoning. It's not some sort of ornamental object added to the theory, but you could actually use it for your set theoretical reasoning. That's ZFC parenthesis L. And then you have one single sentence which says that I is a cofinal subclass of ordinals. This makes sure that I is a proper class. And then you have a scheme which consists of, basically this is the indiscernibility scheme. For each concrete formula phi in the language of set theory, it expresses that I is phi indiscernible. And officially, this is the sentence that we have for each phi. If you have an x1 through xn in I and y1 through yn in I, if x1 through xn are epsilon increasing and y1 through yn are epsilon increasing, then phi holds of the x's if and only if phi holds of the y's. Okay? So this is officially is telling you what is ZFI, but also tells you what is ZFCI. ZFCI, as I mentioned, you simply add axiom of choice to this three sets of axioms. And then if you want to look at the version with the less than, it's just a minor variant. You add a binary relation symbol to the language for global well ordering. Then you have an axiom GW, which stands for global well ordering, which is the conjunction of the sentence which says that less than is a linear ordering and that every non-empty set has a least element in the sense of this less than. It's exactly what you would write down for a global well ordering. And when you have now ZFI with the less than as a subscript, you pretty much go to the previous axioms and just modify it so that they can mention less than. You don't do anything bizarre. So you take the cofinality axiom exactly as before, but then you strengthen ZF, the first axiom group, by saying that ZF holds now in the language L, where L is allowed to mention less than. So this global well ordering can participate in set theoretic reasoning. It can be used in the separation and collection scheme. And also, of course, less than is a global well ordering. And the indiscernibility now takes the stronger form, sorry, oops, that this indiscernibility scheme is now applicable to formulas that mention less than, not just formulas that mention epsilon, which is exactly what you would want to do if you have enriched your language of set theory with less than. Okay, so any questions, maybe as far as anything that might have been ambiguous? I'll just wait for a few seconds.
So PAI is defined similarly to that, where...
Yeah, thank you. Yes, let's go back actually. So here for the first axiom said you have PA in the extended language, which mentions the I. Then you have a sentence which says I is cofinal in natural numbers. And then the indiscernibility scheme would be just like this, except that these epsilons would be less than. Yeah. Yeah.
Okay.
Yeah. Okay. So let's make some basic observations about, like, if one looks at what I've just told you so far, let's see what kind of things one can do with somehow nothing too fancy at the level of just looking at what's known arithmetically and set theoretically. First of all, the standard model of arithmetic does not have an expansion to PAI. That's basically because the standard model of arithmetic is pointwise definable. Every object has a definition, so you will not be able to find indiscernibles in there. But PAI is finitely interpretable in any model of PA, thanks to the schematic provability of Ramsey's theorem in PA. Thus, PAI is conservative over PA, which is something I said earlier. So the idea is that if you give me a finite fragment of PAI, it would just mention finitely many indiscernibility demands. And if you have finite many indiscernibility demands, you want a subset of your natural numbers, which is phi1 indiscernible, phi2 indiscernible, up to some phi 15,000 indiscernible. Then, thanks to Ramsey's theorem, internalizing PA, you can get such an object. That's the first observation. And then if you have a Ramsey cardinal, then one can get outright an expansion of V kappa and epsilon to a model of ZFI. I will not give the definition of Ramsey cardinal right now. Suffice it to say that measurable cardinals are Ramsey, and that the definition of Ramsey cardinals actually makes it obvious that fact number 2 is true. So fact number 2 is just almost falls out of the definition of Ramsey cardinals. Now, what happens with weakly compact cardinals is what happened with the standard model of arithmetic in a way, in the sense that even though the standard model of arithmetic does not have an expansion to PAI, it could interpret any finite subset of PAI. There's always if you give me a finite chunk of PAI, there's a predicate over the standard model of arithmetic, which is satisfying that finite fragment. And the same thing happens with weakly compact cardinals. Any finite subset of ZFI can be interpreted in an expansion of V kappa. So weakly compact cardinal is a strongly inaccessible cardinal such that kappa arrows kappa 2, 2. That's one definition. The other definition, which is equivalent, is that kappa has the property that every kappa tree has a branch. So the analog of Koenig's lemma is true for kappa. And then the other definition involves actually compactness in infinitary languages, which I will not go through. But the terminology goes back to that compactness in infinitary languages. And then combinatorial equivalents were found in the 60s by a number of very nice papers. I think they were, first introduced by Tarski and Kiesler in a paper, I believe in the early 60s, but I would have to double check. Now, every uncountable well-founded model of ZFCI satisfies O sharp exists. Again, O sharp exists is a set theoretical statement, which at this point I don't want to go into explaining what it means, but set theorists think of it as the classical form of showing that V is not equal to L. And now number 4 needs a classical theorem of silver. So if one has that theorem of silver, which talks about a sufficient condition for indiscernibles to exist, then number 4 follows immediately. Now, I would like to contrast that. Let's see, I guess before contrasting it, it looks like I've written number 5, that ZFI is not conservative over ZFC. Remember, because ZFI proves Marlow cardinals exists, but ZFC, of course, doesn't prove Marlow cardinals exist. So that's a big contrast with the piano arithmetic. And then here is this moreover part, which please contrast this moreover part with number 4. So theorem A implies that ZFCI plus V equals to L is consistent, but no uncountable well-founded model of it satisfies V equals to L. So we have a theory which so far is formally consistent, but does not have an uncountable well-founded model. It turns out number 4 can be improved by saying it doesn't even have an omega model. So no, as I will show you, that was, I think, theorem B. So number 4 can be improved using some extra reasoning that this theory does not have an omega model, even though it's consistent. In truth theories, there is a system known as Pfefferman-Sheard system of truth theory, which has a similar fate. It's consistent, but does not have an omega model. Okay, I will now talk about 2 schemes that are actually purchasable, they're provable if you already have either PAI or ZFI. One is the apartness scheme. It tells you that the indiscernibles are far apart. So let me just show you. The way you want to read it is that if you have an I and a j in the set of indiscernibles with I less than j, and if you have a sequence x1, x2, all the way through xn, each of which is a member of V sub I. Remember, each I was an ordinal, so this is just saying if your x's are living in V sub I, and you have an existential statement of the form, there is a y phi of xy, then this existential statement is already witnessed by the time you look at the next indiscernible. If you want to think of it intuitively in terms of functions, if you have a function, a definable function, whose inputs are coming from elements before I, then its output is going to land before J. So hence the idea of these indiscernibles are far apart. And then we have another scheme called the diagonal indiscernibility scheme. In case this terminology structure is familiar, it's the same scheme that is also appears in the usual formulations of the Paris-Harrington theorem. It says that these objects that are indiscernibles are even indiscernible if you allow parameters, not just formulas with no parameters. So you have this strengthened form of indiscernibility, which let me write it down for you. So the way to think about it is that if you fix an I, a particular indiscernible, and if you now pick two other sequence of indiscernibles such that they're both above I. So look at this part, it says I is less than J1. So this sequence J1 through JR begins after I. This K1 through KR also begins after I. So you have two sequences, J1, etc., and K1, etc., both beginning after I. Then we have this strong form of indiscernibility. And what's making it strong is that the indiscernibility is true even if you allow parameters below V of the first indiscernible that you picked, this I. So you're allowed to use parameters from below the first indiscernible. By below, I really mean V sub I of the first indiscernible in your indiscernibility scheme. So what's new here is basically that instead of just having phi of x bar, instead of just having phi of J1 through JR and phi of K1 through KR, we can actually stick in also x bar here in the formula. So this scheme is provable in Z of I. You don't need the axiom of choice. That's why I just wrote Z of I. You don't need the global well ordering, of course, either. And the same proof, but the same idea goes for PAI. I'll just show you, I won't be able to show you the proof of the diagonal indiscernibility because it's rather longish, but the proof of apartness is actually quite quick. It just follows from the collection scheme. And I'm going to give you the model theoretic proof. If you have a model of ZFI, and you fix any indiscernible and any formula with n+1 parameters, n+1 variables, then because of the fact that the collection scheme holds in the extended language and I is cofinal in ordinals, there will be some J0 in the indiscernibles such that if you allow parameters in V of I0, any existential statement that is witnessed will be witnessed in V of J0. This is simply because of the collection scheme and the cofinality of I. And then once you have this statement, because of the beauty of indiscernibles is that if a fact is true of, let's say, a pair of them, then it's true for all pairs. That's pretty much what indiscernibility tells you. If a phenomenon happens locally for two indiscernibles or any indiscernibles, it happens globally for all of them. So that gives you the apartness scheme. And now I think we come to perhaps the first interesting theorem that I can give you a proof of. So far, the theorems that I've mentioned, basically, I just haven't given you any idea of the proofs. And the one I just proved for you, apartness, was quite straightforward. So here, I'll show you how we could buy a truth predicate from the indiscernibles. The way I've written it is actually, this theorem you're looking at the bottom of the page is about piano arithmetic with the indiscernibles. So the claim is that there is a formula in the extended language which gives you a truth predicate. This sigma omega satisfaction class is basically saying that this truth predicate correctly decides sigma 1 formulas, sigma 2 formulas, sigma 3 formulas, etc., etc. So it's the same thing as saying M comma I is a model of UTB. The same proof works for set theory. So here's the truth definition. And the whole idea is to, of course, this reasoning or this construction that I'm just about to describe takes place internally to PAI. Given any formula with n free variables and any tuple of parameters A, we first ignore the parameters A and we look at the formula and write it in pre-next normal form as there exists a V1 for all V2, etc. And then this delta, which is a delta zero formula. And then we write the transform of this first formula phi as phi star to be this modified pre-next form where, as you see, I'm sticking in Z1 and Z2. These are fresh new variables that I'm sticking in for Z1, so there will be no clash with the variables that were there already. So the idea is pretty straightforward. Given a formula phi, write the normal form, and then bound the quantifier prefix by this sequence Z1, Z2, Z, etc. Notice this way we get a delta zero formula. So this
is the quantifiers are correct here in the star. So the first quantifier was existential in phi prime.
Oh, no, yeah, you're right. At some point I had, yes, you're right. No, this is a what Americans call the boo-boo. French call it a faux pas, right? Yes. They should match. I think I had originally, for some reason, had it the other way around, and then I mixed and matched right now. Yes, so they should match. There exists a V1 less than Z1 for all V2 less than Z2, etc. Thank you. Yes. And then now, remember, we also have some parameters. Now, what we do is that we first find J in I, which is the first element of I, which exceeds all the parameters. So that's how we get hold of J. And then we choose the next elements, the next K elements of I to be I2 through IK plus 1. What I haven't, I think, explained to you is what is the K here. So K is basically the number of these Z. So this should be, the last quantifier would be either for O or there exists less than ZK. So these would be Z1, Z2, all the way to ZK. So you have K Z's occurring here. And the idea is that you stick in for Z1, I2, for Z3, I3, and then for ZK, IK plus 1, where the I's are defined this way. Again, to repeat, you find the first indiscernible above your parameters, that's going to be your J, and then let's see. Again, I'm seeing a typo here. So this I2 through IK plus 1 should be also here, I2 to IK plus 1. Allow me to maybe just for a brief moment do something different for a change. I'm going to stop share this, and I'm going to do this. Okay. Can you all see this?
Yes.
Okay. So this is the way it works. So we have. That first line I wrote was supposed to be natural numbers, but let me remind you. So we have a phi of x, which is really phi of x1, etc. And then we have now phi star, which involves not only x, the original free variables,
Mm-hmm.
But it also involves Z1. Sorry for this painful slow, but it's a nice contrast to the slides. Okay, ZK, and there's a K. Okay, very good. Now, if you have some parameter, A, let me call this is supposed to be A, and I'm going to write A bar, because this is a bunch of A's, bunch of parameters which correspond to this X1 that you want to plug in for this X1 through Xn. So what we do is that we first find some I1, which is the first, look at the first indiscernible above your A bar. And then once you have that figured out, then let I2 be the next indiscernible, etc.
Mm-hmm.
IK plus 1.
Mm-hmm.
Very good. And it's actually these guys that we plug into the Z's. So instead of Z1, we'll write down I2, et cetera, and it turns out the indiscernibility scheme and the apartment scheme, in a very straightforward proof, once you have this idea, can be shown to demonstrate that this is actually going to be a truth definition satisfying UTB, meaning that part is just basically following just a very routine induction. This very idea you're looking at right now in this picture was used also in the Paris-Harrington proof. Meaning the truth definition there is somehow quite analogous, except there is for delta zero formulas, here is for all formulas. I'm going to now go back to my original one. Let's see, how do I get now out of this? Okay, let me share my screen. Okay, good. So you can, in a way, ignore this page well, not ignore it completely because there are some typos in it, but the picture that I just drew for you, the idea is that the transform of the formula would be a delta zero formula, which we have a satisfaction predicate for. So, and that's why we get the truth definition. Okay. Are you able to see my my slides right now?
Yes, everything is fine. Yeah.
Okay, good. Okay. And okay, so here basically I was describing the formulation for piano arithmetic. You simply the work here can be easily modified for set theory, and so it's the same kind of reasoning. Now, theorem D is the one which I told you I would give you the complete outline. This was the one which was saying a model of arithmetic has an expansion to PAI if and only if it has an expansion to UTB. So we already saw half of it thanks to this truth definition. So I showed you why if you have a model of PAI, you can get a model of UTB. The other half is actually quite straightforward. If you have a truth predicate, here I'm calling the truth predicate a satisfaction predicate S. So if you give me such a satisfaction predicate, then I can write a single formula with a free variable X, which I'm going to use overspill on. And look at what this formula says. So let me again situate ourselves. I have now a truth predicate satisfying UTB, and I want to show you why we can get this final class of indiscernibles on the model. So look at this sentence. There is a definable, in the sense of S, unbounded homogeneous set for all arithmetical formulas of length at most X. So this actually can be expressed in the language of arithmetic augmented with this S. So basically there's a definable homogeneous set means there is a Gödel number for a formula such that if you consult S, and see what does this Gödel number really mean. If this S happens to be a homogeneous set for all arithmetical formulas of length at most x. So this can be actually expressed in this extended language. And by the schematic provability of Ramsey's theorem in piano arithmetic, for each concrete natural number n, m comma s satisfies phi of 1, phi of 2, phi of 3, all the natural numbers, the standard natural numbers, and therefore by overspill, we can get a non-standard C in the model which satisfies phi of C. And using phi of C, we can then consult S and get our set of indiscernibles. So what's really, of course, important here is that we have a non-standard model. So actually this model, when I wrote every model of PA has an expansion, I should have written every non-standard model. The only model of PA which doesn't have a model, that is a counterexample of this theorem, is the standard model. The standard model does not have an expansion to PAI because I needed to use overspill here. And so this should be every non-standard model of PA. Mm-hmm. Okay. The consequence of the truth definition, now I'm going to shift now to set theory. So I'm going to use this notation of subscripting a model by X, where that means that it's the submodel of the model that are objects that are definable using parameters from X. And this less than M is that global well ordering. That's what you have to have in mind for the case of set theory. So if you have an omega standard model of ZFI with the global well ordering, then so part A and B are kind of gradually build up. So first of all, the truth predicate's definability assures you for each subset of M that is definable in this structure, this M sub X is also definable in this structure. Again, to repeat, M sub X, think of it as the Skolem-Hall of X in the model M. And because you have a truth predicate, you could define Skolem-Halls. And then if you have two cofinal subsets of the model that are definable, then M sub I1 and M sub I2 are going to be isomorphic. This has to do with the fact that both in arithmetic and in set theory, if you give me a cofinal class of ordinals or cofinal class of natural numbers, any two of them, they're isomorphic. So and the model knows it. So if you have a definable subset of ordinals and another definable subset of ordinals, both of which are cofinal in the ordinals, then you could show that they're order isomorphic. And then you can lift this order isomorphism using indiscernibles. So the important thing is that I1 and I2 are subsets of the indiscernibles to the whole Skolem-Hall. And moreover, the isomorphism is definable in the original structure. So far these are kind of, they don't seem to be going anywhere. And then it turns out using these, you could hook up what I just showed you with parts A and B with the theorem of Cunan, which is a very well-known theorem that puts a premium on large cardinals. There's a theorem of Cunan which says there is no elementary embedding of the universe into itself. Basically, it's a theorem of the usual context for this is Gödel-Bernet set theory. So in the Gödel-Bernet set theory, there is no elementary embedding of V from V other than the obvious one, the identity. By non-trivial, we mean it's not the identity. So by hooking up parts A and B, well, really part B, with Cunan's theorem, we buy part C, that there is a non-trivial. Oh, I'm sorry. I went a little fast. Ignore Cunan's theorem for a moment. Part C just follows from part B. I'm just about to, I just went ahead of myself. It's part D that needs Cunan's theorem. So if your model is an omega model and you're a model of this theory ZF with indiscernibles, with the global well ordering, then something part C is saying something very, very important happens. The model can find an elementary embedding of M sub I into M sub I And then by Cunan's theorem, m sub I couldn't be m itself, because if m sub I was equal to m, then it would violate Cunan's theorem. And then this elementary embedding of m sub I to m sub I part C is using a well-known characterization of O sharp following from an elementary embedding of L into itself, gives you O sharp exists, and in particular V is not equal to L. And it also gives you all kinds of large cardinals, which was studied in the papers by Vickers and Welch. Gives you a proper class of almost Ramsey cardinals. This part F is just to give you an idea that it gives you, in the hierarchy of large cardinals, it has large cardinal strength, the omega standard model of ZFI. This is in contrast with just ZFI, whose proof theoretic, sorry, I shouldn't say proof theoretic because it has more than one meaning. Its consistency strength is really below an omega modulo. But the consistency strength of this theory having an omega standard model goes way above omega modulo. It goes beyond V equals to L to the level of proper class of Ramsey cardinals. So I can see now that my time, it's been about an hour that I started. I now would like to use my time economically. So what I have for the rest of the talk is basically a proof outline of theorem A, some variations of theorem A, just one slide which gives you what happens if you modify the hypotheses, and then some questions. So let me consult with Lev. Is it okay if I finish in about 5 minutes or in about 10 minutes? Which one would be better?
I think both are perfect for us. So okay. I will say 10 minutes. We like your talk, so okay. Why don't you speak for 10 more minutes?
Okay, thank you. I will do that, yeah. So the proof outline of theorem A, just to give you an idea of really what are the tools that are used. It uses a number of black boxes, but at least I'll be able to tell you what the black boxes are. These black boxes, of course, are opened up in the paper that is on the archive. So let's revisit theorem A. This is the theorem which was saying that exactly the first order consequences of ZFI with less than is precisely the first order consequences of, meaning in the language of set theory, as ZFC plus lambda. So the proof ends up using a number of facts. I mentioned to you earlier that statement number 2 is equivalent to statement number 3, that GBC plus orders weakly compact proves phi. So this happens to be important in the proof. Also very important in the proof is that GBC plus orders weakly compact has access to a full truth definition for not only V comma epsilon, but V comma epsilon and any prescribed class. Let me briefly explain what I mean by this blue full here. So a full truth predicate in this sense is a truth predicate which decides not only correctly, meaning it not only satisfies Tarski conditions for standard formulae, but it satisfies Tarski's conditions for all formulae that it knows about, even the non-standard ones. So a full truth predicate in piano arithmetic, for example, would give you a system equivalent to ACA, not ACA 0, but ACA. So a full inductive truth predicate. So here we see a huge contrast between ACA 0 and GBC, because ACA 0, first of all, proves that omega is weakly compact, because it's Koenig's lemma. And certainly ACA 0 does not have access to a truth definition for natural numbers, because we can just adjoin all the subsets of natural numbers to natural numbers and get a model of ACA 0. And by Tarski's theorem, none of them was a full truth definition. So here we see a sharp contrast in the set theory and the arithmetical context. Okay, now using facts 1 and 2, one can prove direction 1 implies 2 of theorem A. And I'm just going to quickly walk through it so you get a quick feel for it. So suppose that you have a sentence in the ordinary language of set theory that is provable in ZFI with less than. And suppose that this same sentence is not provable in ZFC plus lambda. then by fact one and the completeness theorem for first order logic, you could find a model of ACA 0 which satisfies not phi. On the other hand, because we're in a model of GBC plus ORD is weakly compact, ORD arrows ORD super n subscript or sub 2 to the power n for each concrete natural number n. And since we could, without loss of generality, assume that our model of GBC is omega non-standard, because we can always find an elementary extension which is omega non-standard, then we have a non-standard C in the model which has this partition property. So this partition property that you see in part 3 is not going to be hooked up with the truth definition to bias indiscernibles. This is pretty much very smooth. We fix a member of, this is a class, this is a collection of classes that we have, which satisfies global well ordering. And since we have the truth definition for every formula, including the non-standard ones, in the collection of classes, we can enumerate all formulae in a way so the ith formula has I free variables. We could do this, of course, by adding redundant variables if necessary. And then we can define an evaluation function. Let me just write down the evaluation function. So this evaluation function, you give me alpha 1 through alpha c. It gives you a long 0, 1 sequence of length c. And the component at coordinate I is going to be 0 or 1, depending on whether, if you plug in this formula, if you consult S, it's going to give you true or not. So you simply consult your truth definition that you had, and you hook up this function, and then because of the partition property that 3 assured us of, we have the set of indiscernibles. So basically, fact 1 and 2, if you have it, once you have it, it's a piece of cake with a little bit of, putting things together. Nothing deep happening besides fact 1 and 2. But the other one, I can just tell you the black boxes for the other direction, 2 implies 1. For 2 implies 1, we have fact 3, which is also in this paper, which is that if you have your model of ZFI with less than, and if you give me an arbitrary linear order that is disjoint from M, and you stretch your indiscernibles, and you get a model M star. So M star is the elementary extension of M sub I resulting from stretching I to the linear order I plus J, where the elements of J all exceeds elements of I. So the idea is that you give me a model of ZFI with less than. I look at I, and then on the top of it, I put J, which is any linear order. And then I by standard factor of indiscernibles, you can form the model which is known as stretching M of I to J. This is just the first thing one learns about indiscernibles is that one can stretch a model M sub I to a model along another linear order. Now, if you do that, then it turns out the second model that you get would be an end extension. And moreover, it has this fantastic property, which is, this is now basically what's really important, that if you had picked your J to be a linear order which has a fixed point free automorphism, for example, if your J was a copy of the integers, which has a fixed point free automorphism, then M star has an automorphism whose fixed point set is precisely M sub I. So you could hook up an elementary end extension of M sub I such that the elementary end extension has an automorphism which fixes everything M sub I fixed, fixes everything in M sub I, but moves everything in that was added on the top. So it's a turbulent automorphism on the new elements, but does nothing on the old elements. So that's fact 3. And then if you hook up fact 3 with something that I had shown back in 2004, that such an automorphism, let me just show you quickly, that such an automorphism buys you basically a model of GBC plus ORD is weakly compact. Then one is able to prove the other direction of the theorem. So in a way, the magic of, I would say, in theorem A is in part 2 implies 1. If I had to kind of pick one direction as a deeper one, it's by far 2 implies 1, which is the deeper one. Okay. Now, some variations of Theorem A is like Theorem A was saying, you know, what happens to the first order consequences of ZFI. Remember, ZFI with less than had an axiom which said that I is cofinal in the universe. One can strengthen that to say I is not only cofinal, but it's also stationary in the sense that it needs every definable closed unbounded set of ordinals. What happens if you have your indiscernibles to be even thicker in a way than just being unbounded? It turns out the first order consequences of that theory in the language of ordinary set theory is just a variation of lambda, which is I call lambda plus, where you simply replace n malo by either n ineffable or n subtle. These are well-known cardinals in the hierarchy of large cardinals with more or less the same proof technique. So one can also ascertain what happens there. And then if you weaken the stipulation that there's a proper class of indiscernibles to the stipulation that there are arbitrary large sets of indiscernibles. So the way you do that is that you instead of a predicate I that is unary, you can have a predicate I that is binary. And you basically say that if you take I and you fix the first coordinate of I, let's say I of alpha comma x, that gives you a set of objects. And you can say that for each alpha, I of alpha x is a set of indiscernibles of size at least L of alpha, for example. You could actually in one scheme write down that there's a proper class of indiscernibles. Sorry, there's a proper class being modified to their arbitrary large. They're basically, you tell me how large you want your set of indiscernibles and I can just find that set of indiscernibles. So it turns out to be conservative over ZFC. That pretty much uses just the Erdo-Gerardo theorem. So this is pretty much at the heart of number 2. And then the other thing which is interesting is that you might want to weaken ZFI by dropping the demand that I is collective. By collective, I mean that when you adjoin I to the universe, the collection scheme is satisfied, but keep separation. So remember in ZFI, yeah, please. I'm not able to hear.
No, you shouldn't hear. I think it's spurious sound, so you continue.
Okay. So remember, the way we have I in this system, ZFI with less than, it can participate in set theoretic reasoning. And what I meant by that is that you could use it in separation scheme and also collection scheme. But what I'm saying here now is that if you drop collection, but you still say, I want to use separation, so you get a weakening of the theory, then that's conservative over ZFC. So this one uses Ramsey's theorem and the reflection theorem, number 3. Let's see, I think I have that was the variations only. And then I now close with open questions. Everything I was saying so far about the consequences was about ZFCI with less than, with the global well ordering being around, but it's not clear what happens if you just stick to ZFCI and ask what are the consequences of it. One would expect that you could use the global generic well ordering to answer this question, but I haven't been able to do that. And I'm now beginning to suspect that maybe ZFCI does not prove lambda. I simply am kind of 55, 45 in this, almost half and half. Which way is this going to go after several months of working on it? The other question I have is, I had in Theorem C shown you the statement that if you have the statement that quantifies both M and N here, then that statement is not provable in GBC. But if you just quantify the top, but leave the bottom to be 2, my proof doesn't work. So it's not clear to me whether this statement is provable with 2 sticking down here in GBC plus orders weakly compact. The arithmetical analog is known to be independent of ACA 0. So if one wants to go by analogy, the answer to question 2 should be, yeah, this should be the case, but my proof doesn't work for that. And then in terms of speed up, there seems to be some interesting questions in the sense that what kind of speed up does ZFI with less than half over ZFC plus lambda? I suspect it has super polynomial speed up, but I haven't been able to close the deal. And for the, especially for the, I think, last question, maybe the first question to answer, which is completely within reach, is PAI. Does it have speed up over PA? It appears to me that the Harrison-Harrington principles have much shorter proofs in PAI than in PA. So as of the moment, I suspect there's a super polynomial speed up, but there are details to be checked that I haven't gotten around to it. And with that, I can conclude my talk with a picture.
Okay, very nice. Thank you very much.
Thank you.
Okay, so now I invite the participants to ask questions and then can unmute, of course, themselves and do so. But also writing in chat is possible. So let me see what do we have. We don't have anything in chat. Okay. Okay, while everyone is thinking what to ask, let me, yeah, you need to gather your thoughts because there was a lot of material which may not be that familiar to participants of the seminar. So this is...
Yeah, exactly. I think that was one of the reasons I brought in at least the PAI story, because I think the PAI story there seems to be still some things to be done about it.
And it also clarifies the analogy that we have here. I think it's very nice when you treat these questions in parallel between set theory and in arithmetic. So that gives you some something to think about. So concerning this, so you had various sort of characterizations of weak compactness here.
Yes.
In particular via this indiscernibility. But so there is yet another classical characterization of it via pi-1-1 reflection, right?
Precisely,
so,
precisely, yes. Yes.
Does it have some, does it play a role here, or is there some analogous
yes, so it turns out
it seems to be like a little bit like indiscernibility, right? So that's kind of relative principle, right?
Yes, actually, in the paper that I've now posted, I've given pretty much an outline, a pretty detailed outline of the proof of also equivalence with pi-1-1 reflection. And so pi-1-1 reflection, meaning GBC plus pi-1-1 reflection is another face of GBC plus orders weakly compact. So in the classical equivalences of weakly compact, it turns out if one opens up the set theory book, there are about typically 5 or 6 very natural, very nice equivalences, which many of them take some work to prove. Some of them go very smoothly in the GBC context, and some of them badly get stuck. And it turns out that the pi-1-1 compactness actually more or less goes through smoothly. There's one known as the Kiesler property, for example, that one has to work very hard at to be able to show. But in a way, maybe the takeaway is that the intuition that one has that weak compactness has many faces in ordinary set theory happens to get replicated in Gödel-Bernet, except that typically one has to work a bit harder and sometimes a lot harder to show the equivalence. But pi-1-1 reflection does not play a direct role in any of the proofs, meaning it's one of those things which maybe is able to, some proofs can be reformulated. Maybe instead of using trees, you can use pi-1-1 reflection, for example. Other than that, I cannot think of a connection that suddenly maybe opens a path that would not be available otherwise in the proofs that we have.
Okay, there is a question from Vladimir Kanovey about references. Maybe you can show the slide with, I don't know, write in chat reference to your preprint or something, keywords or something, how we can find them.
So the title of my talk is Set Theory with the Proper Class of Indiscernibles, and that's in the, if you search for that in the archive,
you'll find.
And there, yes, there the bibliography has all kinds of references there. Yeah.
Okay. Other questions?
Yeah, I have a question.
Fedor, okay.
Yeah. So could you comment about this? How exactly you get zero sharp from the CI on omega model, and more precisely, so how much of induction do you need? So perhaps you basically, if you get a zero sharp from omega model, it means that in some formal settings you need some amount of induction, and then you will get zero sharp.
Yes. So basically, this truth definition that we have in the presence of the indiscernibles, basically is a truth definition that it gives you a model of UTB. So it's well behaved for each standard formula, right? But not necessarily a non-standard formulae. So if your model is omega standard, then so this is where the induction comes in a way, or where the omega standardness comes in. If your model is omega standard, then that truth definition is going to coincide with the external truth definition. And so things being indiscernible internally and externally are the same because our set of formulas are the same. So that's pretty much how the omega standardness is used, meaning the omega standardness using Silver's theorem. So in my earlier slides, I mentioned that if you have a well-founded uncountable model of ZFI, because it's well-founded, of course, then we know that its notion of indiscernibility is the same as ours externally. And so if the model basically is a model of ZFI and the model is non-standard, then you can go to an initial segment of the model using the I, and externally notice that this set of indiscernibles are actually indiscernible over L alpha. There's a theorem of Silver which says if L alpha has an uncountable set of indiscernibles, then you have O sharp. So that's pretty much how one gets O sharp from indiscernibles if your model is externally well-founded and also uncountable. But for the omega standard case, we use a truth definition and the fact that the model can ascertain that there is a elementary embedding of L into itself. There's a permutation of L that then gets you O sharp. So ultimately, it's really in a way, the way to prove it is using the truth definition because it gives you the optimal hypothesis of omega standardness as opposed to well-foundedness.
So perhaps if you really try to write it, so if you get the exact amount of induction, probably so you'll need something like some amount of induction of the language with a truth predicate, something like by one induction, something of this sort.
Yeah, very good. Yes, that's right. That's
right.
Yeah.
Okay. Any other questions from the audience? Perhaps not. Well, then let's thank the speaker once again. Ali, it was very nice to have you with us.
It was a pleasure. Thank you. Thank you very much.